She's in my personal meeting room. Maybe. Uh-oh. I don't see her. Another one. Okay. You're getting here. You're getting here. You guys got any questions for me while everybody's logging in? I'll make sure everybody can hear me, can see the screen. I got some massive sun in my eyes here. We're gonna do some chapter 9 stuff today.
I did the A13 homework.
Okay,
This makes sense, bro. I enjoy this.
good.
About this. But only this.
On the A13 homework, I couldn't figure out how to type it in a way that WebWork wanted.
Okay, like a for instance.
Let me pull it up real quick.
Sure.
Like how do you type in the vector answers?
Typically you type in this little thing here. Okay, wait a minute, I'm not on there. You type in this little thing here, and then you put your components. That's an example of a vector, but you can
Okay,
also write this in terms of 1 times I plus 2 times j plus 3 times k. But I think for WebWork, I think that way would work.
All right, awesome. Thank you.
And that's the less than and greater than symbols on your keyboard.
All right.
Okay, I still have some people saying they've joined in and they're not on my list, so they're going somewhere else. Let's see. Yeah, there we go. Let me give her the Zoom link here. What is the Zoom link? God, it's the one on Blackboard. Let's see. Oops. Wire's in my way. And where's the daggum link? Where do I find this link? Pause recording. Breakout rooms, meeting info. Meeting info. Here's the link. Copy link. Oh, come back here. Send. Send. All right. Okay, now somebody's calling me. Quit that. There's Morgan. Good morning. Wasn't trying to hide from you.
Good morning. I was just looking at the link in the email and not the one on Blackboard.
I thought it was the same one. I copied the same thing. They were
It was a
different?
previous email from before.
Oh, gotcha. Yeah, I tried to fix it so that I had the same one for both of my classes because I kept getting all goofy. Anya wants to know, when is our final exam? Okay, that's a good question. I need to go to Blackboard and find out. Let me see. I'm going to get my calendar pulled up here. I got Friday, December 4th. believe that's the first day of finals. And it's at 10:30. And it runs until 1 o'clock. And what I did last time that we had this online crapola is that I made the final exam open notes, but not open internet.
You mean Wolfram Alpha can't take my exam for me?
And no matter how hard you try, that would be considered cheating. Those Wolfram answers are so goofy, it'd take me forever to grade it because I'd have to figure out how they got what they got and if it's the same as mine. I think it's fair enough to say using your notes. But I'll let you use your notes so that you don't have to memorize any kind of formulas anymore. You can use all those notes that are on Blackboard, provided that you have them as notes.
Is it comprehensive?
I'm sorry?
Is it comprehensive?
It is comprehensive.
Like the whole semester?
Yep. I don't believe it's departmental anymore, but if I get a hold of the guy that makes the departmental exam, he writes good exams. So if he sends me one, I'll probably give you his. And there will be no corrections. It's open notes, so no corrections will be taken. And we'll review for the final on Wednesday. This same location. Maybe I won't have the sun so badly in my eyes. Let's see, what else? What else you got for me? I got 13 participants. Where's everybody else? Okay, then let me remind you what we were talking about. We were talking about in chapter 9. We were talking about vectors in R2, which is our Cartesian plane, and in R3. So R2 is just the XY plane. So we have a vector, say, from the point P to the point Q. We write as vector PQ. And if we know the coordinates of those points, we can find that vector. Say point P is located at the ordered pair 1, 2, and point Q is located, I don't know, that looks like at about 5, 3. Then to find the form for vector PQ, we put them in these cute little brackets here. You take the difference in the x's from terminal point, the one at the tip of the arrow, to the initial. So we do 5 minus 1 in the x direction and 3 minus 2 in the y direction. So that's the vector 4, 1. We can also associate that with a position vector from the origin. So if I put a point at 0, 0 and then count over 4 and up 1, I get a vector of the same length parallel to vector PQ. So I'm going to call this the position vector associated with PQ. Has the same length, it just has its initial point at 0, 0 and its terminal point at the ordered pair given by that. We also have a couple of vectors called the standard position vectors or the standard basis vectors. when you guys take linear algebra, you'll talk about bases for different spaces. In a two-dimensional vector space, the standard basis vectors would be the I vector that corresponds to the vector whose x component is 1, whose y component is 0, and the j vector. I put the little hats over the vector instead of the arrow, 0, 1. On your test and on handouts, we'll have bold print to denote vectors as opposed to variables. So the standard basis vector, if I draw it on here, there's I and there's j. And the idea is you can write any vector in terms of linear combinations of these, like vector PQ can be written as 4I plus 1j. So you'll see both writings. When we talk about three-dimensional space, three-dimensional vector space kind of looks like this. I'll draw the there's the y-axis, there's the z-axis, and then we draw the x-axis coming out of the page and then going back into the page. That one's the x-axis. I don't want that anymore, I just want that. So x comes out of the page, y is here, and z is there. And our standard basis vectors, we would have the I vector here, j here, and then we have another one called k. So I is the vector 1, 0, 0. J looks like 0, 1, 0. And then the k component goes up and down in the z direction, 0, 0, 1. So a vector like 4I minus j plus 2k could be written like that or like this. And as a position vector, I can draw it for you. I would go out 4 units in the I direction where this little red line is 1 unit. So if I go out 4 of those, I'm here. And then I go to the left 1 in the y direction. So I'm back over here, and then up 2 in the k direction. So it's coming out of the page, and there's that vector right there. Call that vector v. And we said last time that we have basic operations of vectors. The operations that we had last time is that you can add vectors, you can subtract vectors, and you can multiply a vector by a constant. So for instance, v plus w, let me just take this vector v from here, 4, -1, 2, and let's make w be the vector I plus 6j minus 10k. And so if I write it component-wise, it would look 1, 6, -10. And addition of vectors is done component-wise. A vector plus a vector gives you another vector. It gives you 4 plus 1 is 5, -1 plus 6 is 5, 2 plus -10 is -8. Subtraction's done the same way. You subtract component-wise, so 4 minus 1 is 3, -1 minus 6 is -5, and then 2 minus a -10 is 12. If I multiply a vector by any constant, if I just use the k here, what it does is it multiplies each component by k. And if k is a positive whole number, it makes that vector k units longer. So those were the obvious operations. Today we want to talk about 2 more operations. Let me point out a few things first. We've got the magnitude of a vector was its length. And we would denote the magnitude of a vector by putting these little bars around the vector. And you find the magnitude by squaring the components. So in our example, it'd be 4 squared plus -1 squared plus 2 squared, and then the square root of that. So we get 16 plus 1 plus 4. I get the square root of 21 as its length. If you take any vector and divide it by its magnitude, you get what's called a unit vector, a vector of length 1. This would give me a unit vector in the same direction as v. So all I do is I take each component of vector v and divide it by the square root of 21, and I'll have a vector whose length is 1. Okay, so this vector has magnitude equal to 1. That's what we mean by unit. Magnitude equal to 1. So I think that's all the stuff that we did last time. Does that sound any bit familiar? If I multiply by a minus sign, it gives you a vector in the opposite direction. If I want to change its length, then I first find a unit vector, and then I multiply by whatever length I want it to be. So if I want a vector in the opposite direction, of v in my example, but with magnitude of 10, then I just take, to get it in the opposite direction, I put a minus sign in front of my multiplier. Come on, page, turn. So I put a minus 10 here, change direction, change its length, and then I multiply it by that unit vector. So we get negative 40 over the square root of 21, positive 10 over the square root of 21, and negative 20 over the square root of 21. So it's just a matter of learning the language. The operations themselves are pretty dang simple. Geometrically, the addition of two vectors follows the parallelogram rule. Parallelogram, oh, can't spell it, P-A-R-A-L-L-E-L-O-G-R-A-M. Suppose I have vector V, and I'm drawing them as position vectors, added to vector W, then vector V plus W is the diagonal of the parallelogram with sides V and W. So I'd have to first finish my parallelogram. So if I take the vector W and draw it out here, oops, that doesn't look very parallel. Let me try a steadier hand here. Well, that's not a heck of a lot steadier than that one. Vector V plus W, I'll draw in red then, will be this diagonal here. And in physics, we call that sum of the two vectors the resultant force. If our vectors represent force, it describes where the object moves to if it's got a pair of forces in the direction and magnitude of V and W pulling on it. Let's see if I remember what the difference looks like. Who remembers that? What does V minus W look like? Let's see if this is vector V and this is vector W. I think vector V minus W is here. I think that's the way it goes. Does anybody agree with that? I don't remember if that's correct or not. Any of my physics people agree with that? Yeah, really, who cares what it looks like, right? Okay, all right. Let's go over the two more operations that we have. There are two different versions of multiplication. One version of multiplication is called the dot product between two vectors, and the dot product between two vectors gives you a vector that is a scalar quantity. Scalar meaning just a simple regular old number. So if I take a vector whose components are A1, A2, A3, and I literally put a dot right there, like our multiplication dot, and then B1, B2, B3, the dot product is a scalar. It's the number you get when you take A1 times B1 plus A2 times B2 plus A3 times B3. And so, for example, if I take the dot product between 3, -5, I just said, and 10, can you guys hear my dog snoring back there? Man, he snores like an old man. I guess my math lectures put everybody to sleep, including my dog. Okay, so
How are
this,
your cats?
oh, I had to put that old one asleep. So she's out in the backyard under a few feet of dirt.
Jeez, I'm sorry.
I know, it was tough. It was tough, but it was time for her to go. All right, so here's my dot product. So according to what I wrote above here, I just multiply the two x components together, 3 times 2, and get 6. Now I add -5 times 1 is -5, and then I add 10 times 3, 30. So the two x components, 3 times 2 plus -5 times 1 plus 10 times 3. So here I get 36 minus 5 is the number 31. All right, so my next example was taking the dot product between these two-dimensional vectors, 2, 0, dotted with 0, 5. And we get 2 times 0 is 0, and 0 times 5 is 0. So one thing I wanted to point out here is we have something called a zero vector. It's a vector whose magnitude is 0 and has no direction and no magnitude. It's a vector. So when you talk about the zero vector, we can put this little hat on it. That's different from the zero scalar. Oops, sorry, I don't get a vector, do I? I get, in this case, a scalar, because it's a dot product. So I get 2 times 0 plus 0 times 5. So I get the number 0. So note that 0 is a scalar, and 0 with the bar on it is a vector. So 0 with the bar on it in 3 dimensions would look like that. So some things about the dot product. Let's look at what happens if you dot a vector with itself. Let's take the vector 3, -5, 10, and dot it with itself. And what we would get is 3 times 3 plus -5 times -5 plus 10 times 10. So if I write it like this, then maybe you recognize that as being the stuff that you do inside the square root sign when you're finding the magnitude of a vector. The magnitude of the vector is the square root of the sum of the squares of the components. And so I'm going to write it like that. You get the answer here first. 9 plus 25 plus 100. So that's 125 plus 9 is 134. So for any vector v, v dotted with v is going to be the same as its magnitude, but without the square root sign. So I put it as v squared. And since the dot product gives you a scalar, the order in which you multiply doesn't matter. Dot products are commutative. That's not going to be true when we do a cross product. And dot products are also distributive. If I'm adding two vectors together, and then I got another one that I want to dot it with in either direction. See, v plus w is a vector. So if I take another vector and dot it, let me think of a letter. Let's take a u. Then I can distribute that as a u dot v and get a scalar, plus u dot w and get a scalar. So scalar plus scalar is a scalar. So I can find the sum first and then the dot product, or I can distribute. So we've got the commutative property and the distributive property. And then the other thing is, I did the verification on the little video that I sent you, but the dot product can be used to find the cosine of the angle between two vectors. So if I want to find the cosine of that angle, or even find that angle, I can use the law of cosines and the magnitudes of vectors. And if you want to see the proof, it's in the video that I linked in your email, that v dotted with w divided by the magnitude of each vector, because remember, cosine is a number between 1 and -1. That's equal to the cosine of the angle between two vectors. In calculus, that angle is in radians. So I'm not sure if on web work they ask you for radians or degrees. If they ask you for degrees, then you have to multiply this by 180 over pi. And that tells me that if this angle is a right angle, if theta is 90 degrees or pi over 2, cosine of that is 0. So if this number on the right-hand side here is 0, then that means the numerator is 0. So we have that if theta is pi over 2 or 90 degrees, then v dotted with w is 0. And it's not even, not just an if then, it's an if and only if. So let me put a two-headed arrow here that says if the dot product is 0, then the two vectors are at a 90-degree angle or perpendicular to one another. If two vectors are perpendicular, then their dot product is 0. So I'll say that in words. Two vectors are perpendicular. And another word for perpendicular is orthogonal. If and only if, their dot product is 0. Zero the scalar and not 0 the vector. So these are listed as facts about dot products. The vector dotted with itself is the magnitude squared. The dot product is commutative. The dot product is distributive. And one of our favorite applications of the dot product is that it gives us the cosine of the angle between two vectors. From that, we can decide whether two vectors are orthogonal if and only if their dot product is 0. I've got a couple of examples here that I'd like to go through. These are from the little worksheet that I linked to you. Tried to download that worksheet 1,000 times on this stupid iPad and I couldn't get it to go. So I got to write them. It says find V dot W if in part A, I don't even have a part B, so why would I want a part A? So let's get rid of the part A. If V is 2i minus j, and W is 3i plus j, and then I put a k component on here, plus 4k. So if I don't list a k component for vector v, then it's implied to have a coefficient of 0. So it's easy to do. All you got to do is remember that you're going to get a scalar. I'm going to write it out with the sharp brackets. I'm going to write vector v as 2 minus 1, 0. And now vector w I'll put over here as 3, 1, 4. And now we multiply component-wise. 2 times 3 plus negative 1 times 1 plus 0 times 4. And so I get 6 minus 1 plus 0. I get the number 5. Easy enough? All right, my next example says, find the angle between, so when I say find the angle, find the measure of the angle between the vector whose components look like minus I plus 2j plus 4k, and the other vector is 5i minus j. And after we find the angle between them, are these vectors perpendicular to each other? So here's my symbol for perpendicular. Not just my symbol, everybody's symbol. Okay, so we're going to go back here to this page. And there's the formula that we're going to use to find the cosine of the angle. And then if it's an angle, if it's a number we recognize, then we can say the number. Otherwise, we'll use the inverse cosine function. So let me write the formula down. The cosine of the angle between two vectors is their dot product, v dotted with w, divided by the length of the vectors in the operation. So in our example, I'm going to write it out, negative 1, 2, 4, dotted with 5 minus 1, 0. And now let's put their lengths down here. To get the magnitude, I take each of the components, square them, add them together, and then put them under the square root sign. So negative 1 squared plus 2 squared plus 4 squared under a square root sign. And then down here, 5 squared plus negative 1 squared plus 0 squared. Okay, so let's knock it out. On top, I have negative 1 times 5 is negative 5. 2 times negative 1 is a negative 2. 4 times 0 is 0. on bottom, I have 16 plus 4 is 20, plus 1 more is 21. And here I have 25 plus 1 gives me 26. So it's not an angle that I know. I get minus 7 over square root of 21 times square root of 26. And so if I want the angle, then I write the inverse cosine of that number. Okay? And so to answer the question, are these vectors perpendicular to each other? Well, this number is clearly not 0. I'm sorry, theta is not pi over 2 because the dot product is not 0. And that number up there is not a 90-degree angle. Let's see if there's any questions anywhere. So far, no questions. Feel free to butt in anytime you want to. Number 3, we want to know our vectors 2, 0, negative 3, and 1, negative 2, 1 perpendicular to each other. So we take their dot product and look at the size of the dot product. Here we go. 2, 0, negative 3, dotted with 1, negative 2, 1. So I take 2 times 1 is 2. 0 times negative 2 is 0. Negative 3 times 1 is negative 3. So we get negative 1, and so the answer to our question is nope. Nope, would have been had I put a negative 2 here. So there's our dot product. Dot product is a scalar, and the dot product can be used to find the angle between two vectors. There's also another application of the dot product. Did I cover it in this handout here? I don't think I did, but I want to. So we must. I wonder why I didn't put that on this sheet. We got something called projections, vector projections. I don't know why I didn't put it on here. Let's see. Let's see if this is vector V, and this is vector W. Sometimes we're interested in finding the vector projection of vector V onto W. Geometrically, it looks like this. If I drop the perpendicular down here, then it's this vector right here that would be essentially the shadow if the sun were at high noon. That's the projection of V onto W. And the way we write it as, we write PROJ, projection of vector V, put vector V down here, onto W. Let's see if I remembered how to find that. The projection of V onto W. So what I need first is to take W and scale it down to a vector of unit length. And so that would be W divided by its length. And that's a vector. This is a unit vector in the same direction as W. And then what? And then let's see if I remember how to do this. I never remember formulas. Then I need to multiply this by a vector that has that length. So I need to put some sort of scalar here. So here's the unit vector. And that's going to be a dot product of V with W. And then I need to multiply it by the magnitude of W. So this stuff here that I'm putting the parentheses around is a scalar. It's the scalar that describes this length. And then I multiply it with this vector. So a scalar times a vector gives a vector. That scalar that I have in parentheses is called the scalar projection, or sometimes called the component. Of V onto W. So this dot product divided by the magnitude of W multiplied with this unit vector gives me the projection of V onto W. And it comes from the law of cosines, because if I put an angle in here, not the law of cosines, comes from right triangle trigonometry. That's a right angle there. That number there is, see, the cosine of this angle is the adjacent side divided by the hypotenuse. And so that adjacent side, the cosine of theta is equal to this length, which was some version of W divided by the magnitude of W times the length of vector V. So this is given by the magnitude of, well, let me take that away. That length, let me just put it right here. This length is the magnitude, come back here, pencil. Magnitude of vector up here, V, times the cosine of theta is that length right there. And from above, the cosine of theta was the dot product between the two vectors divided by the length of the two vectors. And then so if I divide it by that length, then I'll get my projection. So that's where this little formula comes from. We use projections a lot in engineering and in physics. May have written this backwards. Projection of V onto, I think I want the W down here. I think I've written it backwards. Let me make a quick peek in the book. V onto U. Yeah, I did write that backwards. So let's put the W vector here and the V vector here. Because I was going to say the way I remember the formula when I half-ass remember it right here is the one that's down here is the one that's down here. Whatever's down in the notation is the one that's down in the denominator. And it's the vector that we're projecting onto. And again, we use the vector projection of V onto W a lot in engineering and physics. So that we can get things back into the same tangent plane when we're talking about this stuff being on surfaces. So it moves things down for us so that we can kind of look at what it's going on to. So in our example, let's go ahead and find, so let's make example 4, find the projection of, let's use V as being our vector up here, 2, 0, -3, onto W, which was our 1, -2, 1. And so I'll write the formula again. I'll write it right here. The projection of vector V onto W is V dot W divided by the length of W times W times the length of W. So sometimes they put the lengths of W together and write that as the magnitude of W squared. And sometimes, like we said up earlier, the magnitude of W squared was the dot product of W and W. Sometimes that's listed as W dot W. But it's easier for me to remember if I write it like this. And so, let's see. V dot W we found earlier. V dot W we found up here as being -1. The magnitude of vector W we found earlier, maybe. Let's just put it right here. 1 squared plus -2 squared plus 1 squared. And then we multiply it with vector V divided by its magnitude. And so I have a -1. This number is 4, 5, 6. Square root of 6 times the square root of 6 is just 6. You can leave your answer here, or you can distribute the -1/6 through. -2/6 is the same as 1/3, and then another -1/6. I don't know why I didn't put that in the chapter 9 notes. I guess it's not that important to know, but I want you to at least see it once. Let's see how we're doing on time. We've got plenty of time. Okay, so the next operation that we've got going on between two vectors is called, another application of a dot product. Let me do one more application of a dot product. Okay, so another application of a dot product is work. Remember back at the beginning of the semester, we said work is done if a force is applied to an object and the object moves a certain distance. So work is going to be a number, a measure of this force and distance. So work is done when a force, a vector force, is applied to a distance. So say we're moving an object from point P to point Q. So we've got an object here at point P. It's going to have some sort of force applied to it, causing it to move, say, to a point Q. So it's the number that we get in this dot product. Measures of work were foot-pounds and joules. So it depends on how these are measured. If force is in pounds and PQ is in feet, then our units of work are foot-pounds. So those are the ones I'm familiar with. If we're in meters and what was the other thing? What goes with a joule? Meters and don't know.
Newtons.
Newtons, meters and newtons. Then we've got joules. If we've got centimeters and ergs, then we got something else. So I'll go with pounds and feet. So find the work done. Find the work done by the force 6I plus 2J plus 3K acting on ACTING on an object if the object moves from point P at 0, 2, 4 to point Q 5, 6, 7. So from up there, work is a number that you get by taking the dot product with the vector from P to Q. So if I write these in the sharp brackets, that's 6, 2, 3, dotted with, now let's get vector PQ. Remember, you take the terminal point minus the initial point component-wise. So 5 minus 0 gives me a 5 in the x component. 6 minus 2 gives me 4 here. And 7 minus 4 gives me 3 here. Now our dot product is the number 6 times 5 plus 2 times 4 plus 3 times 3. 6 times 5 is 30, 2 times 4 is 8, 3 times 3 is 9, 30 plus 17 is 47. So let's assume that these are pounds and this is feet. And so that would be our foot pounds. Okay, so 3 applications of the dot product: the angle between the two vectors, the projection vector of one vector on top of another, and then the work done. And pound it into your head over and over and over and over and over that the dot product is a scalar. Our other version of multiplication is going to be called the cross product. And those of you who've done cross products before, everybody has their own way of doing it. I'm just going to go the by the book way. So suppose I have a vector, in my notes I called it vector A. I'm going to use a capital A. Capital letters as the names of my vectors. No, I don't. A cross B. So we use like our multiplication symbol. Where vector A has the components A1, A2, A3, and vector B has B's as those components, B1, B2, B3. If you look at the formula, it's kind of complicated looking, but it gives you a vector whose I component is A2 times B3 minus A3 times B2. That's the I direction. And then minus A1 times B3 minus A3 times B1 in the J direction. And then plus A1 times B2 minus A2 times B1 in the K direction. But there's no way to remember that formula from that version of it. Here's how we remember it. We set that up as a 3 by 3 determinant, kind of a special determinant. We haven't had determinants yet, so I'm going to draw it out. We put these vertical bars here. Then we put the generic basis component vectors here, I, J, K. Then whatever vector is written first, you put its components in the first line. So I said vector A has as its components A1, A2, A3, and vector B has its components B1, B2, B3. And the way that you compute this determinant, it's a 3 by 3 determinant. And you'll learn in linear algebra a bunch of different ways to compute this determinant. The definition of it is that thing that I've written above, but if we picture it, if you take your finger and cover up the first column and the first row, you get a 2 by 2 determinant. The 2 by 2 determinant you get has A2, A3, B2, B3 in the I direction. Then if you erase that, let me see if I can erase that. Boom. And next time, cover up the second column and the second row. Oops, didn't mean to do that. I want the first, not the second row. I want the second column and the first row. That leaves these 4 numbers uncircled. Those 4 numbers go in the next determinant in front of the J. So I'd have an A1, A3, B1, B3 here. And there's something called the Checkerboard Principle that says as I move across the first row, I change the sign. So I would go plus, minus, plus. So that's why a minus is there in front of the J component. And then finally we do it again where we cover up the first row, but the third column. And then those 4 numbers are in the plus determinant, A1, A2, B1, B2 of the K component. Then to compute the 2 by 2 determinants, you multiply the diagonals, A2 times B3 minus the product of the reverse diagonals. So that's where the A2, B3 comes from here, minus the reverse diagonal. Then the minus sign here from the checkerboard principle. And again, A1 times B3 here, B1 times A3 here. Lastly, plus A1 times B2, A2 times B1. You subtract. So you make the, if you set up your determinants like that, the cross product is easy to remember, but remember the cross product of 2 vectors is a vector. And it's not just any vector. The cross product between 2 vectors gives a vector perpendicular to both of them. And I don't know if I can show this on the little camera, but if I use my index finger and my middle finger as the 2 vectors that I'm crossing, and then I stick out my thumb, you get a vector that's perpendicular to both of them. And then there's some sort of thing called the right-hand rule that I never can get my right hand to do, to tell you whether that vector is pointing up or pointing down. You'll get that in your physics class. You won't get that from me because my thumbs don't work that well. But anyway, the cross product between 2 vectors gives a vector that's perpendicular to vectors A and B. So A cross B is a vector perpendicular or orthogonal to both vectors A and B. And so here's what we're going to use it for in Calculus 3. We're going to try to write the equation of a plane. And to write the equation of a plane, you need to know some version of its slope. And that thing that's going to give its slope is a vector that's perpendicular to all vectors in the plane. So if I take vector V in the plane and vector W in the plane, then their cross product is that vector that's perpendicular to all the vectors. So I'm using A's and B's. A cross B will be called the normal vector to the plane. There's one and only one plane that contains both vectors A and B, their cross product gives the normal vector to the plane. So after your first, couple of weeks in your vector calculus class, you'll have computed cross products in your sleep. You're just going to do cross products like crazy. So I want you to walk into your Cal 3 classes knowing how to do that. Don't be that student that doesn't know how to do a cross product. So let's do a few. Let's find 2, -1, 3 crossed with 0, 7, -4. And you've got to do them in order. I'll show you in a minute why that's true. The claim is that this cross product gives a vector perpendicular to both the vector 2, -1, 3, and 0, 7, -4. So after we find this cross product, let's use the dot product. Then, I can't write neatly, then use the dot product to show that this vector is perpendicular to both 2, -1, 3 and 0, 7, -4. For you non-believers out there. Okay, so we're going to set it up as a determinant. So I'm going to put it down here with the cross between them so you can make sure that you pay attention to which one goes into which row. Okay, so we put our I, J, K up here. You can put the little hats on it, because that's one of the good things about math is that you can put hats on your variables. Now we've got the 2, -1, 3 right in here, and then 0, 7, -4 there. And these bars mean we're going to compute a determinant. Now I'm going to expand this in terms of the 2 by 2 determinants. So I don't know that you are not going to be able to see my finger covering up the rows and columns, so I'll draw the red lines on them again. So my first 2 by 2 determinant, I cover the first column and the top row. And then I write the 4 numbers that are left as a 2 by 2 determinant, -1, 3, 7, -4 as the I component. Always remember the middle term is going to be minus. Next, I cover up the first row, second column. So those are hidden underneath my fingers. And I see the 2, 3, 0, -4, which I'm going to write in the next determinant as the J component. And we have plus. All right, let's take that one away. We're going to cover up the third column. And then put the 2, -1, 0, 7 as the 2 by 2 determinant in the K direction. Okay, so we've got now these 3 2 by 2 determinants to compute. So we do that by first multiplying these two numbers together. -1 times -4. Yeah, let's just write it. And then you subtract the reverse diagonal, 7 times 3. And that number goes in front of the I. So for the next one, I've got 2 times 4 minus 0 times 3. So 2 times 4 minus 0 times 3 in the J direction. And then plus, I've got 2 times 7 minus 0 times -1. 2 times 7 minus 0 times -1 in the k direction. So let's see what I got here. I've got 4 minus 21 is a negative 17. Then I have 8 minus 0 with the minus sign in front gives me a minus 8j. And then 14 minus 0 with the plus sign in front. And so there's our cross product. Now, to show that this vector is orthogonal to both of the original vectors, we take this vector and dot it with those two. So let me write it in the sharp brackets. So let's take it. Dot product can be done in any order. So I'll put it first. And I'm going to take its dot product with 2, -1, 3. So I get 2 times -17 plus -1 times -8 plus 3 times 14. So 2 times -17 is -34. And then plus 8. 3 times 14 is 12. 3 times 4 is 12, 3, 42. Uh-oh, so I did something wrong. I'm supposed to be getting 0 out of this. So what numbers went wrong? 2, -1, 3, 0, 7, -4. That's 4. Minus, who's caught my mistake? 4 minus 21.
In J, shouldn't
J.
the 4 be negative, so it should be plus 8?
Oh God, I lost a sign right there. Okay, let's make that a negative. That a negative. That does make that a plus 8. So let's make that a plus 8. And that then would be a -8. My hero, you found it. So there's -42 plus 42 is 0. Who saved me right there? Who was that? Morgan? Atta baby. All right, now let's do it again. We're going to do the dot product with that and 0, 7, -4. Come on, page, turn for me. So I'm going to take -17, 8, 14, and dotted with the other vector, which was 0, 7, -4. So -17 times 0 plus 8 times 7 plus 14 times -4. So that's 0. 7 times 8 is 56. And that's a -56. So again, we get 0. So the moral of the story is you can always make a quick check if you did your cross product correctly. Do a quick dot product and make sure that you get zeros out of your dot products. All right, I'm going to give you a minute to do the next one by yourself. I want you to find the cross product between -I plus 2j plus 4k and 5i minus j. Take a minute and see if you can find that cross product. All right, I'm gonna catch up with you then. Set my 3x3 determinant. So the top row just has your I, J, and K in it. Those are just the symbols. Then the first vector, you put its components in row 2, so -1, 2, 4. And then 5, -1. And since the K component's missing, you have to put a 0 there. Now we set up our little 2x2 vector. So if I use my fingers now and cover up the I column, I have 2, 4, -1, 0 in the I direction. Remember the minus sign for the J. -1, 5, 4, 0, the J. And then plus -1, 5, 2, -1, K. So I have 0 minus -4. And then I have -1 minus 20. And then I have +1 minus 10. Those are parentheses. And so I have 4i minus a -21 gives me +21j minus 9k. So let me make a quick check. That's -4 plus 42 minus 36. 42, 36 and 4. Oh, did I do something wrong again? 1, 2, 4, 5, -1, 0. So that's 0 minus 4. It's a negative, okay. And then minus 0, 20. Oops, that's 0. There's my mistake. That's a 0. And so that's just 20. And then again, I've got 1 minus 10 is a -9. So now let me check my answer by doing a quick dot product. That's -4 plus 40 minus 36. Now I got it. Everybody else get that? Any questions over what we're doing when we're doing this cross product? All right, I'm going to show you what happens when you start flipping things around. Let's change the order. Let's find 5i minus j cross, oops, I don't need to do that brackets around there. Crossed with, I did the brackets up there too. Boy, that's goofy. Those should be parentheses. I don't need both symbols. Parentheses. Let's change the order in which we've done this. Minus I plus 2j plus 4k. And so here's what we're computing. This time the 5 minus 1, 0 goes here, and -1, 2, 4 goes here. So on your mark, get set, go. I'll race you. So that's what you should get. And what do you notice of the two vectors that we get when we cross them in another order? You get the same vector with same components, but opposite in sign. So note that, oops. Any two vectors say V cross W will give you the same as W cross V, but in opposite direction. That's going to be true with any determinant you compute. You're going to compute determinants in Cal 3 and in linear algebra. And if you interchange any two rows, it changes the sign of the determinant. So the order matters. It's no longer commutative. Now what I want you to notice is what happens if you cross a vector with itself. So I want you to compute minus I plus 2j plus 4k crossed with itself. Take a minute and do that cross product. Let's see what you discover here. So what you should notice is you get the zero vector, not the zero scalar, you get the zero vector. Okay, so if ever you're doing a determinant and any two rows are the same, that determinant has a value of 0. Okay, so note that any vector crossed with itself is going to give you the 0 vector. All right, one more example here. I want you to find a unit vector, that is a vector of length 1, that is orthogonal or perpendicular to the vector 5, -1, 4, and the vector 3, 0, 1. Find a unit vector, a vector of length 1, that is orthogonal or perpendicular to two stated vectors. So you have to go back to our definition that the cross product between two vectors gives that orthogonal vector. So we're going to find the cross product. Then we're going to take our cross product and we're going to make it a vector of length 1. So we've got two steps here. Get the cross product to get the orthogonal vector, and then make it into a unit vector. cross product is. Get you used to the notation. Like that. I'll write this step out. If you just do this part in your head, I'm okay with that as well. But again, the more work you show, the better chance it is to get partial credit. So I'm covering up the I column and writing the 4 numbers that remain in the bottom right-hand corner. Make sure you get the minus sign for the J, cover up the J column so that you have a 5, 3, a 4, 1. And plus the K column, so cover up the 3rd column. You have 5, 3, negative 1, 0 for the K component. Okay, so I get negative 1 times minus 0 is a negative 1. Then I have 5 minus 12. 5 minus 12 is a negative 7, so this makes that plus 7. And then I have 0 minus 3, so minus 3k. Then I'll do a quick dot product with one of the vectors. So with the first one, I get a negative 5. Minus 7 is a negative 12. Yep, negative 5. Minus 7 is a negative 12. Uh-oh, I blew a sign somewhere. Oh, right here, that's a positive 3. 3 times negative 1, and that's the reverse diagonal. So I need to keep doing these dot products. So I've screwed up every single cross product that I've done. And since a dot product is easy to do, it doesn't hurt to do it. So I took my cross product and I dotted it with my first vector, and that's how I caught that I missed that sign right there. But that gives me my cross product. Now to get the unit vector, so our second step, we make this a unit vector. By dividing by its magnitude. So the magnitude of minus I plus 7j plus 3k is the square root of negative 1 squared plus 7 squared plus 3 squared. So 49 plus 1 is 50. I get the square root of 59. And so the vector we seek is the vector minus 1 over the square root of 59, I plus 7 over the square root of 59, j plus 3 over the square root of 59, k is the unit vector we seek. Okay. Anybody want to say anything? Questions, comments, complaints? Everybody happy? Okay, so let me put all these things that I wrote and read earlier as properties and put you some more properties here. So here are some properties of the cross product. Let's change. All right. So the first one was that any vector crossed with itself is the 0 vector. If you change the order in which you cross them, V cross W is the same as W cross V, but opposite in sign. Whether I put it on the first vector or on the whole thing, it changes the sign. So I'll just put it on the whole thing. There is a distributive property. If I take a vector and I cross it with the sum of 2 vectors, I can add the vectors first and then take the cross product, or I can do a pair of cross products and then add the two vectors together. So it's like distributing the U and the cross operation through the parentheses. That's only through addition and subtraction. Can't do it through anything else. There's a law of signs that tells us the next one, that V cross W divided by the magnitude of V, magnitude of W, which looks a lot like that dot product thing, but this time it would give you the sine of the angle between two vectors. Gives you the sine of the angle between two vectors. By itself, the magnitude of V cross W gives you the area of the parallelogram with sides V and W. This is vector V, and that's vector W. The parallelogram I'm talking about is this one. And so the magnitude of V cross W gives you this area inside here. If you cut the parallelogram in half, then you have a triangle. So 1/2 the magnitude of V cross W is the area of a triangle with sides V and W. There's even a third one. If I did a, it's called a triple product. A cross product gives you a vector, and then if you dot it with another vector, then that number, screen froze for everyone. Okay, how do I fix a screen freeze? Let me reshare. Hang on, let me see if I can.
Whatever you just did fixed it for me.
Oh, everybody's good? Okay, I didn't do much other than click. I took my magic wand and waved it. Good? Okay, so what I wrote down was that V cross W is the area of a parallelogram with sides V and W. And then if you cut a parallelogram in half, you have a triangle. So this triangle here has area of 1/2 of V cross W. And then I was talking some more that there's a 3-dimensional version of this. That if I take the cross product now and I compute a dot product with it, let me write this down. If I compute this thing here, U dotted with V cross W, I guess I'll make the claim first and then I'll state it. V cross W is a vector. If I take that vector and dot it with U, we get a scalar. One way to get the scalar is by brute force. Another way is to compute this numerical determinant. Suppose the vector U has as its components U1, U2, U3, and here's vector V's components and W's components. This gives that triple cross product, which can also be written as U cross V dotted with vector W. We'll do that to show that it works with some random vectors. And then let's compute this first, and then I'll make a statement about it. So let's grab us 3 random vectors, u, v, and w, and show you how to compute this 2 different ways. So, for example, let u be the vector whose components are 1, 2, 3. Let's use v and w from before. Let v be 5, -1, 4. And w, let me see what that one was. That one was before 3, 0, 1. And let's compute u dotted with v cross w both ways. First way is let's take v cross w that we found a few minutes ago. That was the vector whose components were -1, 7, 3, and form its dot product with u. And then let's compute this 3 by 3 determinant, which I'll have to show you how to do. So the first way is take vector u and dot it with what we got from v cross w, some from before. V cross w was, let me switch my page here, v cross w, 5, -1, 4, 3, 0, 1 was the vector -1, 7, +3. So let's put that in here. Now do this dot product by multiplying the 2 I components together, plus the 2 j components, plus the 2 k. Remember, we get a scalar. And I'm getting -1 plus 14 plus 9. So 13 plus 9 is 22. Now the second way is the claim that those two, that this dot product, let's use u dot v cross w, is the 3 by 3 determinant. And so I would put the components of u here, which were just 1, 2, 3, and then I put v, which was, where's v, 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 5, -1, 4, and then 3, 0, 1. So we're going to do it the same way, but instead of putting i's, j's, and k's outside the determinants, we're going to put 1, 2, and 3. And it'll be ordinary number multiplication. It won't be any vectors. So I would have, if I cover up the first column, -1, 4, 0, 1 times the number 1, and then minus, cover up the second column, 5, 4, 3, 1 times the number 2, and then plus, I'll cover up the third column, 5, -1, 3, 0 times the number 3. So these determinants give me -1 times 1. And here I have 5 minus 12. 5 minus 12 is a -7 times 2. And then here I have 0 minus a -3, so 3 times 3. And so I have -1 minus a -14 plus 9, and there's what I got before. This triple product, when the number is positive, that you get out of this triple product, I'm multiplying 3 things together with our 2 versions of multiplication, dot and cross. that number that you get, if it's positive, can be interpreted as the volume of, it's not really a box, it's a parallelepiped. It's a box whose base is the parallelogram given by V and W, and whose height is given by the vector U. So you can think of this number here as the volume of the parallelepiped. Ooh, that's a cool word. If I can only spell it, P-A-R-A-L-L-E-L, parallelepiped, P-I-P-E-D, I couldn't spell it, parallelepiped with base V and W and height U. So if I try to draw my three-dimensional thing here, V and W, make that into a parallelogram, and height of U. So it's this box, except for it's not a box because the base is a parallelogram instead of a rectangle. Gives you that volume. If you get a negative number, just take the absolute value of it. So you can just say that the volume is equal to U dot V cross W. And I'm not going to go into the geometry of it. I'm just going to tell you and you're going to believe me. So let's see. Back up here. Where are my properties here? So you can add the third one, that the absolute value of this is equal to the volume of the parallelepiped. Whose sides are V, W, and U. But make sure you take the absolute value of it. Okay. So we are going to use, yes, go ahead.
Can you go back to the other page with the properties?
That one?
Nothing changed.
Nothing changed. We frozen again?
There we go. It changed.
Oh, okay. Well, there's a lag.
Thanks.
Okay. So what I want you to know out of this section is I want you to know how to find the magnitude of a vector. I want you to know how to add and subtract vectors and that the sum of two vectors is a vector. I want you to know how to compute a dot product of two vectors and know that that tells you, that can be used to tell you the cosine of the angle between two vectors, because it's important to know whether or not two vectors are perpendicular. Well, speaking of perpendicular, how do you know if two vectors are parallel? What makes a vector parallel to another? There's a vector. There's a vector. How do I know that they're parallel?
Would you use the cross product over the magnitude times the magnitude when that equals 1?
Right, from our V cross W divided by the magnitude of V, magnitude of W, gives us the sine of the angle theta. And so if the vectors are parallel, then technically the angle between the two of them, if the sine of theta is 0, then it means that the vectors are parallel. And so that happens if the numerator here in this formula gives me that the cross product in magnitude is 0, right? Because sine of 0 is 0. But it's even easier than that. A determinant is going to be 0 if any two rows are the same, or if one row is a scalar multiple of the other. So two vectors are parallel if you can get one vector by multiplying the other vector by a scalar. So for example, if vector v was the vector 1, 2, 3, and vector w was the vector 5, 10, 15, then I got this vector w by multiplying everything here by 5. So vector v is parallel to vector w. So you can eyeball it. You don't need to compute the cross product. If one row is a multiple of another in a determinant, then your determinant is 0. Or if one vector is a multiple of the other, then the vectors are parallel. Okay, so two vectors are parallel if one's a scalar multiple of one another. Two vectors are orthogonal if their dot product is 0. And again, orthogonal is the same as saying perpendicular. So again, I was trying to tell you the things that I need you to know. I need you to know how to compute sums, differences, dot products, cross products. Find the angle between two vectors either by using the cosine formula with the dot product or the sine formula with the cross product. They both are talking about the same angle. And be able to determine if vectors are parallel or orthogonal. You'll use that vector projection thing next semester in Calculus 3, but I don't think that that's one of the main things that I want you to get out of this. Add, subtract, dot, cross, find whether they're parallel, find whether they're orthogonal, be able to compute magnitude and unit vectors, those kind of things. So I hope that when I put a question with parts on your final involving stuff from chapter 9, that it's giveaway points for every single one of you. What do you think?
Sounds good.
Sounds good? Okay, well, one of my favorite games in all of history is the game where I write down some stuff and ask you if what I'm writing down is a vector, a scalar, or neither, something that's not even possible. So we're going to play the vector, scalar, neither game. Ooh, if you were 21, we could make a drinking game out of it. Maybe we can just all get a big old glass of chocolate milk and play the chocolate milk chug game. So vector, scalar, or neither. Okay, so when I talk about, I'm going to let V and W and U are all vectors, and C and K are scalars. Okay, so can I do V cross W dot U? That's my first contestant. Vector, scalar, or neither.
That would be neither, right?
That would be neither, right? Because?
Because you can't cross a vector with a scalar.
Good. This is a vector. This is a scalar. And this is a vector operation. So I can't cross a vector with a scalar. So this one is neither. So everybody chugs, except, who was that? Daniel? Chug your chocolate milk. Okay, how about if I put V dot W cross U? Swap places with the dot and the cross.
That'll be a scalar.
Be a scalar because V cross U is a vector. That's a vector. And the dot product between two vectors is a scalar. Good. All right, how about V cross W cross U?
Vector?
It is a vector. Cross product is a vector. The cross product between two vectors is a vector. And a vector cross a vector is a vector. Told you this game was fun. I can just hear you rolling and having a good old time about it now. Okay, how about V dot W plus U?
Scalar?
It is a scalar. Sum of two vectors is a vector. Vector dotted with another vector is a scalar. How about V dot V cross W dot W?
Neither?
It is a neither. This is a scalar. That's a scalar. Oops, can't spell it. I still can't skip, but a cross product is a vector operation. I can't cross two scalars, so this is a neither. Okay, so I think I'm out of time, just about. Oh, I've got about 8 minutes. But I'm out of page here. So what I would like you to do is make sure that you can do all the web work problems. Okay, so make sure you get your web work done. If some of you want to improve web work scores or go back and do some of the web works you weren't able to do, send me an email and I can open up some web work for you, but not too much because I want you to start preparing for your final. The study day is, what day is the study day? Is that Thursday? Because the last day is Wednesday. Wednesday is the last class meeting. So I'm going to do my best to update the grade book as much as I can. So those of you who are finished with web work, I'll try to get your web work grades in. If you turned in all your write-ups, I'll try to get all of that computed by Wednesday. In our last class meeting, we're going to review for the final. So I want you to look over your old exams. And those of you who did a paper exam for me, I'm going to try to go into the office and scan them and send them back. Those of you who did an electronic copy, I've already sent yours back. So look over all of your old exams. And I will try to put the keys, I will put all the exam keys on Blackboard. They're not there yet, but I hope that I can put them there. We had somebody in the main office test positive for COVID, so they closed the office to sanitize it, and they weren't letting anybody in. So I couldn't do any of this before Thanksgiving, and I'm hoping that they'll have the office open today so that I can do my scanning. But go over your old exams. I'll put the keys on Blackboard, and I'll go into detail, and I have some review problems that you can practice. I will put a copy of the old exam. I will put an old final on Blackboard for you to practice. Oops, forget vowels. I'll put an old final for you on Blackboard, and then you practice it. And then we'll practice a little bit of stuff on Wednesday. And our final exam is again on Friday at 10:30. So it's time for you to blow off your other classes and just concentrate on calculus. Many of you have got an A, solid A going into the final. I'm never the kind of person to tell anybody what grade they need to make to get an A in the final. I figure that's a math problem, and so you can figure it out, your math students. So I'm not going to tell you what you need to get an A in the course or a B or anything like that. Those of you who are missing exams, make sure you send me an email and let me know when you can take your makeup. Anything else do I need to tell you? I'm supposed to tell you to fill out the online teaching evaluations. All of you should have gotten an email by now. So do that. At least so that we know how crappy this online stuff is. Hopefully next semester things will be back to normal, our old normal. Anything else? Are we done for the day?
Thank
Okay,
you.
I'm gonna let you go. If anybody needs to stick around and ask me anything, I'll stick around, but the rest of you may go and have a wonderful day. Okay.